Okay. Any questions about the equations we've developed so far? And remember what the equations were. I'm just going to say them out loud. W times e to the I beta minus 1 plus z e to the I alpha minus 1 equals delta. That's the loop equation for dyads going from one position to another. Okay, the equations solve very nicely for a 3-position problem. Okay, and so that means we're going to write 2 versions of that equation. A version that goes from position 1 to 2, and a version of the equation that goes from position 1 to 3. Do you remember, enough about the equations, first of all, do you remember the knowns in the synthesis problem that show up in those equations? The alphas were knowns, because those are the change in angle of the rigid body. That's also the change in the angle of the upper vector that's attached to the rigid body. So we have 2 alphas to start the problem, and we either have 3 points, or we have 2 deltas. 3 points very quickly lead to 2 deltas. Okay, that's what we started the problem with. Then we have those 2 loop equations that we can solve, and we're going to guess the betas is our strategy for getting solutions. We don't know them. We don't really even care too much about what they are, but we're going to guess them to try to find solutions. So now we've got to remember which mouse to play with and which screen to play with. Let's look at a Mathcad document for landing gear synthesis. And the first thing I'm doing is entering the critical data for synthesis. P1, P2, P3, alpha 2, and alpha 3. Can't start synthesis without that. Would you agree? All right, can't do anything without that. Now, for synthesis to make sense, don't I need some pictures? Because I've got some legal and illegal zones in this problem. And if I can't see my legal and illegal zones, then I can't judge whether designs are even acceptable or not. So these are my arrays here of points that would make up the airframe or the wing. That'd be the legal and illegal zones within the wing. And then these are the points that will let me make a picture of the landing gear. And so here is the airframe, and that never moves. And here's the landing gear that's going to move through 3 different positions. So now I can make sense of my answers. I said P1, P2, P3. Let me very quickly get to the deltas. I get to the deltas because I need the deltas more than I need the P's. Question so far. Is this making sense? Okay. I said we were going to use sliders to choose our betas. Okay. And I have 1 slider for beta 3, and I've got 1 slider for beta 2. And what I claimed was when I pick a particular value of one of these and then plot all possible values that flow from the other one, I'm basically looking at an infinity of solutions, right? Now what I chose to do is let beta 3 choose which infinity I'm going to look at. So let me move the screen a little bit more and we'll see something. Actually, I'm going to reduce the size for a moment to try to get more on the screen. May not be able to read it as well, but we can get more on the screen. Okay, there is a blue circle, at least an arc of a circle, I think you would agree. And it may be distorted by my aspect ratio because I probably need to be just a touch wider, at least on my screen. This 2 to 4 looks smaller than that 2 to 4. How does it look on your screen? Same thing? Let me widen this up just a touch. And then maybe the circle things will look a touch more circular. Still need to go further. 2 to 4, 2 to 5, I don't know. That's still not looking as circular as I would like. But in any case, I said if I change one of the betas, that changes my infinity of solutions. Do you see how as I move the slider and let go, I'm getting different infinities? Okay, do you see 2 infinities of solutions on that? Or do you see 1 infinity of solutions on that screen? Okay, and every time I change beta 3, I get a different infinity. Now, what happens when I change beta 2? Do you see that black line? Remember, these points have to correspond to each other. Okay, so there's a particular blue point that corresponds to beta 2 equal 189 degrees. And there's a particular red point that corresponds to beta 2 equal 189 degrees. And those 2 points have to stay together to make a machine. I can't use this blue point and that red point down there if they don't correspond to each other. They have to have come from the same beta 2. So by moving my beta 2 slider, I can look at different solutions. Do you see the black line moving? So those are my individual solutions. Now remember what I said about good and bad solutions. I might have good solutions if the grounded circle passes through the grounded area and the moving circle passes through the moving area. I might have good solutions possible, but then again, there may not be any good solutions, and even in that picture. Why might there not be any good solutions? And the answer is the legal blue solutions may not have a black line moving to the legal red solutions. They may not correspond to each other. All of the legal blue solutions may point to red solutions that are outside the legal bounds. Now, how useful are these circles and is this picture without having the airframe and the landing gear on this picture? Can we tell what's good and bad in this picture? Okay, we're wasting our time with this picture, aren't we? Okay, that's absolutely right. And I wanted to show that. Now, let me take this one. I'm going to copy it so I don't lose it. And I'm going to paste it right here. And in a moment, we're going to come back and look at some details of what's going into all of this. But right now, I just want you to sort of see the mechanics of it. Paste. All right. Are there any legal solutions in this picture? Okay, now, you also need to know what red means and what blue means. And to be honest, I've forgotten, so we're going to go find out. The red stuff is the A0 points. The blue stuff is the A points. Which ones are moving, A0s or A's? A's move, so the blue is the moving pin joints, and the red is the grounded pin joints. Are any of the red points in the legal zone? Lots of them. But are any blue points in the legal zone? None. So how many good solutions are there? Do I need to even move the beta 2 slider to see if any of these hook up right? No point. What do? I need to move the beta 3 slider. Now, I chose to let beta 3 give me the big picture, and beta 2 give me the detail. Could I reverse that? Is there a priority here that would matter conceptually? No, but this is just the way I set it up. Controlling beta 3 controls the circles that I see. Controlling beta 2 lets me pick the particular solution that I see. So I need to move beta 3 some, and let's see what happens as I play with it. Okay, first of all, do you see that I am moving blue toward the right area as I'm moving left? Let me start again. I'm in the middle. As I move left, do you see blue getting closer and closer to the right area? Okay. At this point, is it possible that I have a viable solution? Is it guaranteed that I have a viable solution? No, why not? Because I may not be able to get the black line to go from this point to a legal red point. How will I know that? I play with the black line. And I start, oops, wrong mouse button. I just start moving it arbitrarily to see which way things go. Oh, there's some promise. Now, do you see how the blue is moving fast and the red's hardly moving? Okay, why is that? It's because the points don't have uniform density. Can you see the blue points bunching up right about here and being very sparse out here? You see the red points bunching up in the middle here and being very sparse out there? That's just the way it is. So I keep moving. What do you think? Do we have any hope? Is this one going to work? No, why not? Because red's not moving enough. Okay, and I've got blue in the range, but red's not in the range. So I don't believe there are any legal solutions in this picture. How quickly are we learning all this stuff? As compared to get out a pencil and paper, pick a beta 2, pick a beta 3, crunch the numbers by hand, look at that one solution Oops, no good. Change beta 2, change beta 3. Crunch it, look at that one solution. How long would that take? Probably infinity to the fourth power years. So that'd be a lot. So without a computer, this solution, this method stinks. Okay, but with a computer, we can learn a lot very fast. So what would you propose I do to make this search? Maybe, which way should I go? How about I keep going left on beta 2? I'm sorry, keep going left on beta 3. And now that I've got a black line roughly in the area, okay, I'm going to sort of leave it there, and I'm going to go play with these and see if any will work. And it's still not moving very much. Oh, look at that. I moved beta 3 just now, and look at the black line that I left behind. We are very close to legal, aren't we? Now, are we legal? Let's say I'm not quite legal. Let me move this to the left just a touch. And which way did things move? It's moving. Okay, I'm not sure I'm really within what I see as the square. I'm within the beige picture, but I really want to be within this square here. And I think I just moved outside the square. So if I move back just a touch, is that solution legal? Clearly a legal solution. So now, how many solutions? We've been looking at every picture, which is an infinity of solution. So we've been searching through an infinity squared number of solutions. Okay, every time we change one, we're searching through that infinity. Okay, why did I say infinity to the fourth solutions, not at -1? Why not infinity squared? I need another link. I need a left side and a right side for the mechanism. And so I've got infinity squared possible solutions for the left and another infinity squared possible solutions for the right, all coming from the same infinity squared solutions combined together. Why -1? Infinity to the fourth -1. How come? Can't have the same solution for both sides. Okay, good. So there's a solution. Is it a great solution? Maybe, don't know. How are we going to figure that out? Got to pair it up with another. Now, I can't animate this, right? Okay, I've got to pair it up with another solution and then decide two things. Is it, even after I've picked two that look good here, they look perfect here, why might they still be unacceptable? If I picked two separate solutions out of here that look perfect, why might they still be illegal? Say that again? Okay, and they don't move smoothly, and here's what I would say. They don't actually touch points 1, 2, and 3. They may only touch points 1 and 2, and it might miss point 3 completely. Okay, so why could that be true? I explained that last time. Why might what looks like a good machine here not actually pass through all 3 points? Remember I talked at the end of class about branches of a mechanism, how a machine, and since I can't draw on the computer right now, a machine, and I'm going to draw it in this position because I think it's easier to see. Yeah, that's big enough to do that. Okay? This link can rotate 360 degrees, right? It should be able to rotate continuously. This is going to move up and down, rock back and forth. Okay? This is on one branch of the machine. If I take this pin out, I can actually move this mechanism to another branch of the machine, which would be down here. Could this lower machine operate? Let me just spin continuously. Yeah, it's going to be just as happy as the upper machine. Okay, but it may be that I can't move smoothly from one branch to the other without actually taking the machine apart. Now let's think about what our dyad synthesis equations say. Did the dyad synthesis say anything about what happens in between my two key points? No, it simply said it is in point 1 and it is at point 2. Here's the vector relationship between them. It can be assembled in all 3 positions, is all the dyad synthesis equations guarantee. So even though the solution might look perfect here, it may totally miss one of the points. First one, the second one, well, it won't miss the first one because we're going to make sure it hits the first one. It might hit the second one, might miss the second one, and might miss the third one because mechanisms have branches, and although it can be assembled in the third position, it can't actually reach the third position without being taken apart, so it goes somewhere else. That will be a test question. Those of you who are here today have no excuse for missing that test question when I ask you why a mechanism that looks like it was synthesized beautifully, the math was done right, everything looked great, just does not go through the positions. And it's because of the branches of the mechanism, and it's because the equations only guarantee assembly in the three positions, not motion between them. Okay? Now, what would I want to do to get another solution? Could I just move my slider over a tiny amount? Oops, that mouse doesn't work. Can I just move this over a tiny amount and say, there's a second one, let me call that one legal. It's close on the right-hand side. Let me declare that one legal. Can I use that one and the one that I had just a moment ago to make a 4-bar? What do you think? Mathematically, yes, I can make a 4-bar, and that 4-bar might in fact move it through all three positions. What's wrong with having two links incredibly close together? Can you think of anything like that? Stability? Tell me what you mean by that. There's several meanings and several of them are right.
Well, if your links closer together, it won't take as much force probably.
Okay, so the statics, the force transmission through two very closely spaced links could be very bad, and that is precisely the right answer. Now you use the word stability, which I don't know if you meant it this way, but let's say I've got this 4-bar, moving that machine. Can all of you see that now? Okay, and I apply a large side load to this thing, and now I've got to resist that with motor torque. I think you can see that the static force is what would probably be horrible. Now here's the other thing that's happening. Probably one of these links is now in very high tension, the other link is in very high compression. What's wrong with high compression in structures? Buckling, and buckling is a stability issue, and so your choice of the word stability was in fact very good. This link may go unstable because of buckling unless I make it very, very thick. I think the force transmission in this machine would be lousy. So what I want to do is spread out my solutions to come up with something that is probably better. Now, can I keep my beta 3 and spread out my solutions a lot with this particular problem? I don't think so. So how am I going to go find other solutions? Now let me back up. Do I have to find two solutions that both have the same beta 3? Do I have to find two solutions that come off the same circles? No. Matter of fact, I almost certainly don't want to find two solutions that come off the same circles. I probably want to find solutions that come off radically different circles because that moves them further apart. So let's go explore a little bit more. Let's just move further to the right. All right, and, sorry, to the left, the other left. Okay. Am I guaranteed to have any in there that work? No guarantees, but I can go explore. Let's see what happens. Okay. Technically, I guess that one's legal because it is left of here, or right of here, and it is above that line. It's technically legal, but it's probably sticking up. There's probably another illegal zone, isn't there? Somewhere above the top of the wing, it probably goes illegal again. So I'm going to rule that one out. So I don't know that I'm going to find another great pair over on the left side of the beta 2 slider. Therefore, what might I do? The middle didn't look good. Let's go see what the right, just go explore the regions. And probably the first thing you ought to do when you're ready to start hunting is don't worry about this slider, the second slider, very much. Just go explore. See what the far left looks like. See what the far right looks like. See what the middle looks like. That kind of stuff. Starting to sound like a political science conversation. But so here's the far right. Are there any possible solutions far right? Let's see, I've got red in the legal zone, I've got some blue in the legal zone. But I'm going to tell you what I really would wish for. I got a nice solution that ran from the right hand side to the bottom. Sure wish I could find a solution that comes from the left hand side. Now, there might be some here. I don't know if they're in the right region. Let me try to put a few more solutions on the left hand side. That doesn't appear to be doing it. That's doing it. Now let's see if any of them are going to match up. And I showed you my designs. I've obviously found some that behave the way I like. I don't remember precisely where they are. Okay, but this is looking promising. This is looking incredibly promising. Okay, I don't love that one so much. But how about that one? That one is in both legal zones. It's a solution on the left-hand side that's radically different than my right-hand side solution. I think I put those two together, and I think I may have a pretty good machine. What do you think? You see how the search goes? How hard is the search? For this one, not too bad. Is it possible some... Now, what if I really tightened up my legal zones? I made it much smaller. Might I make the search harder? Sure. Okay. And so some other problems with tighter legal zones compared to how the machine has to move might make the problem harder. Just means you have to spend a little more time searching. Any questions? Let's say that I were just going to give you this as a software package and ask you to go find semi-promising designs. Could you do it? Okay. And could you explain to another good engineer who understands complex numbers and vectors, could you start with a picture and explain the equations to them? If you can do that, you understand what I want you to understand. Now let's go look at how this thing is working, and I'm going to show you a little bit of new Mathcad. Okay, first of all, see this line right here? This line's hiding code. I double click on it, and here's the code that was hiding. What was the value in hiding that code? Got my sliders closer to my picture is the value of hiding that code. Okay, and so this thing is called a region. Insert, let's see, let me click right. Oops, not sure what that's about. Click right there. Open up a little bit more space. Insert, where is it? I want to insert a math region. No. I want to insert an area. Why isn't it letting me? Am I already in one? This is weird. Make a little bit more room. Should be insert area. Okay, I guess you have to have enough room to insert the area. When you insert the area, and now let me go back to 100% display because it's not showing everything well. When you insert the area, it gives you two lines. You can click on it. Let's see. You can click on it and move it. You can make the area bigger or smaller. Double click on it, it's hidden. And I'm going to hide this one too. Double click on it, it's hidden too. I can reopen this one and type hello world. And then I just want to put something in there to show you that I can close it and reopen it. Okay? The other thing, so that's a handy technique that you can expand or collapse to hide things. Creating a slider. I'm going to click right here, and is it under insert, control, and look, we can do check boxes, radio buttons, push buttons, a text box, a list box for choosing things, or a slider. So I'm going to insert a slider. There is my slider. Notice there's the colon equal sign to the upper left. Now there's no way to do sliders with global equal signs. Why would I maybe have wished for a slider with global equal signs? Then I could put it right next to the graph and not have to use that hidden region, but apparently you can't do that. Okay, so XXYY is the name of that variable controlled by the slider, and if I print out XXYY equals, it's equal to 0. I slide it a bit, it's equal to 26. I slide it a bit, and it's equal to 100. What's the default range of a slider? 0 to 100. Let me see, do I double click on it, or I think I right click on the slider, MathSoft slider, I think it's edit. Okay, maybe it's not edit. Maybe it is properties. Properties, orientation, horizontal or vertical. Point bottom right. I'm not real sure what that means. Can show tick marks, tick frequency. Here's the most important thing probably. Minimum value of 0. I set my maximum value to 360. And so, let's see. What are the, I don't know what that means. Point bottom right. I'm going to see what both does. I have no idea. Apply. Apply. It changed the look of the button a little bit. I don't know what that means. There's a help system. You can find out what that means. That may just be appearance. I don't know. The thing that matters the most is the value. And so now we're going to go from 0 to 360 on the slider. And I can make it longer if I want to by grabbing the black box and make the slider as long as I want to, making things look reasonable. When you open a document like this that has a slider in it, it believes that sliders are dangerous for some reason. It could cause a virus or cause some harm. It asks a misleading question. When you pop up open a document like this, it says, you got stuff in it. Do you want to disable it? And the natural answer is yes, I think. If you disable the sliders won't work. You have to re-enable them. So when you open the document, it says, do you want to disable your sliders? Say no. There is a way to enable and disable these things. Let me see. I'm going to right click. Disable evaluation. The slider, excuse me, the slider no longer works. Right click. So if you disabled them when you open the document, you just have to go find your sliders and re-enable them and they'll work again. Or you close the document and reopen it and say no that time. Any question about sliders? Okay. Let's look at the graph and then we'll look at the guts. Okay. I've put the stationary airframe on the graph. No problem with that. You can draw a picture and you can put it on a graph, right? I've put my landing gear moving thing in position 1 on the graph. That was drawn up at the top. No problem. You can do that too, right? Now, what am I putting here? I'm putting what must be an array of points named PA0. And these are my A0 points. Okay? And let's see. So I'm putting my PA0s imaginary and real. That would be my array of red points, which means I got to calculate an array of red points, right? We'll go look at that in a minute. I've got my array of point A's, which means I've got to calculate those. We'll look at that in just a minute. This is easy, this is easy. My black line is drawn using a variable called link. What does link look like? Link equals, it's 2 complex numbers, which means 2 points, right? Takes 2 points to draw a straight line, so no great shock here. Link is a straight line composed of 2 points. Which 2 point? An A0 point and an A point that correspond to the same subscript value that came from the beta 2 that I selected. Okay? So you think if you had these arrays, you think you could do this graph? I believe you could. Let's go look at the math involved now in doing the computation. It's hiding in this region. And let me wipe this out, all of that, so I don't lose all that space. That's gone, and let me collapse this region by mashing on the delete key for a little while. Okay. Let's see if there's anything between my initial definitions and my sliders. Document starts with pictures that are going to be useful to me. Legal grounded stuff, legal moving stuff. My critical data for starting the synthesis that controls the motion. Calculate the deltas. Choose my betas in advance before I even need them. I'm going to get rid of that stuff too. Now, this is a number called 307. Surely that means degrees, right? That number 333, surely that means degrees. I've eventually got to convert this stuff to radians for it to make sense, right? Sort of. Okay, I'm going to first of all take beta 3D and multiply by degrees to convert it into radians. Doesn't that sound just wrong? Okay, but that's, if you look at the value of DEG, multiplying by DEG, we'll take this number and convert it into radians. So now beta 3 is in radians. Limit is 360. I goes from 0 to limit. And beta 2 sub I goes from 0 to 360. But by multiplying by degrees here, that is converting this beta. This beta 2 is in radians. Okay? And so here's my infinite number of beta 2s. I'm just creating them. Okay? This is my particular value of beta 3. And remember, what I'm showing with the circles is one value of beta 3 generating an infinite number of solutions that come from beta 2. So here's my one value of beta 3, my semi-infinite number of beta 2s. Do you remember in looking at the picture? Well, we ought to be able to drop down there. I don't have very many points in that region. In fact, how many points are in the region that spans this distance? Say it again? No, there's an infinite number. In reality, there's an infinite number of angle points that span that region. There's a whole infinity of solutions right here. What if I didn't like any of these 5? What if I wished for a solution right between those 2 points? Is there such a solution available? Sure there is. I'm just sampling coarsely with 360 points, but it's just a sample. Could I jump my sample up to 7,200 or something like that? Okay. Could I shift all my samples by half a degree so that my beta 2 goes in half degree increments? That would just sort of shift the whole circle thing by half a degree, wouldn't it? So realize there are an infinite number of solutions in here. If I don't like what I see here, I could go tweak the math a little bit and I could get more solutions in this region. It's just that I'm sampling, but there's in fact an infinite number of solutions there. Okay, going back to the equations, I have my beta 3. I have all the beta 2s that I want to use. I'm just printing out my deltas here. Don't remember why I printed them out, but I did. This thing right here represents my 2 equations, 2 vector equations, expressed in linear solver form. And we wrote this out by hand, didn't we? Okay, but this equation right here implies that W, e to the I beta 2 minus 1, plus Z, e to the I alpha minus 1, equals delta. And it implies 2 sets of those. They've just been repackaged in the linear form using the matrix inverse. This matrix, I'm going to go ahead and copy it and print it out. Actually, it's going to have so many copies because of the value of I. Let me do it anyway. I'll cheat for a moment. Control V equals, it's too many, but if I say I colon equal to 5, okay, this is nothing but a matrix of complex numbers. Okay, if I look at a particular value of this thing, it's a matrix of complex numbers. Can I invert a matrix of complex numbers? Well, I apparently can because I did. But let me go ahead and do that. Let me click on the palette and take its inverse. And there's the inverse of that matrix of complex numbers. That's part of where Mathcad is speeding things up for you as compared to doing it by hand. Because although I could teach you, once I remembered how to do the inverse of a 2x2 matrix of complex numbers, I could teach you how. I'm not going to bother to. Mathcad does that so nicely. We're just not going to bother. Okay, let's get rid of that. Get rid of that. Okay, this is my two vector equations, two vector unknowns. All of the scalar stuff is known. The deltas are known. Those are known. That's my only unknowns. What comes out of this thing? First of all, it does have an I subscript right there, doesn't it? And right there. How many times will this equation run? 361, because I goes from 0 to 360. This will run 361 times. It's going to give me 361 W's, and it's going to give me 361 Z's. Okay? If I take the W's and Z's, of what use are they to us practically? Not much. We don't really care about the W's and Z's. What do we want to do with the W's and Z's? We want to go back to that P1 and back up to get point A, and then back up through another vector and get point A0, right? And how many times do we want to do that? 361 times. So point A is P1 has no subscript on it. It's my key point that I'm trying to control and move. Point A sub I is P1 minus Z sub I. Then point A0 sub I is the point A sub I that I just computed minus the W sub I. And it's the I that connects these two solutions together. So PA5 and PA05 go together. Can I form a mechanism that legitimately that involves point A number 17 with point A0 number 20? No, they don't go together. They weren't a common solution of the machine. So I've got to, and that's what drawing that black link does. It keeps them correlated together. Finally, I'm going to draw link, and I haven't used beta 2D yet. I've used beta 3D right here to get my particular value of beta 3. This, I just got all 360 values of beta 2s. I never used this. Where am I going to use this? Simply to draw the black link. That's its only purpose, is to pick out one solution out of the infinity and draw it. So finally I say the link that I'm going to put on the picture is going to use that number as my subscript, and I'm going to use, in this case it's 333, so I'm going to look at point A number 333, and I'm going to look at point A0 number 333 connected together, and that's the black line that I'll see. The only effect of this slider is to change the particular pair of A's and A0s that I see connected by that same variable. That, computationally, is everything. What do you think of the complexity of the computation other than having to invert a 2x2 complex matrix? Pretty simple stuff, isn't it? I will expect you to be able to do by hand absolutely every computation in this document except inverting this matrix and taking the inverse and multiplying by the deltas. So I'm going to expect you to be able to do everything by hand except this one equation right here. Now, when I say everything except this one equation, what's left? Okay, well, what's left is I expect you to take the P1s, 2s, and 3s that I give you and do vector subtraction and come up with the deltas. Anyone scared yet? Okay, you can do that. You can do this, right? Hope this isn't scary. If this is scaring you, it's time to drop the class. Okay, take P1, 2, 3. P2 minus P1 gives us delta 2. P3 minus P1 gives us, and I expect you to remember that it's 3 and 1, not 3 and 2. Do we go from 2 to 3 in the equations? Never. Could we? Maybe. Maybe we could have, but that's not the way we set it up. So I expect you to be able to take these 5 numbers and do that calculation. What's next? I don't expect you to do that calculation, but I sure expect you to be able to do this one. What does this say? It says point A is the P1 that I started with minus the particular Z value that I just got back. What is Z going to be? Z is going to be a vector. Okay, so that means Z is going to be a complex number. P1 is a complex number, right? Z is a complex number. Doggone it, you got to subtract complex numbers again. Okay? Okay, what do we have to do here? Take the A you got there, put it right there. Find that complex number for W. Doggone it, we got to subtract complex numbers again. What math do I expect you to be able to do by hand on a test? Subtract the right complex numbers from each other to get the right answer. And that's not the hard part. What's the hard part? knowing which complex numbers to subtract. Okay? That's the level of math I would expect you to do by hand for this synthesis thing. Okay? And that's it. That's all the math. Any question about the math or the way it's put together in Mathcad? Let's see how we're doing on time. We got about 3 minutes left, so that's not bad. What I'm going to do is give you this document that solves the landing gear problem in printed form, actually PDF form. Okay, so I'm going to actually ask you to solve a synthesis problem, but I'm going to ask you to create the document yourself, because that gives you a better chance of actually encountering the equations and understanding the equations if you at least have to type them in. And there's not nearly as many equations in this thing as there were in the position analysis document. Okay, what would be the logical next step, though, once I have... Now, first of all, what am I going to want to remember out of this document? I'm going to want to remember, and let's see, I'm not necessarily printing them out here. Once I find a link that I like, don't I want to remember its grounded pin joint A0 location and its moving pin joint, point A location? Those are what I would want to write down, and those are contained in this variable link that I just printed out, because link is, and I'd have to go look at it. One of them is the A0 point and one of them is the A point for this thing. And it looks like the top one must be the A point and the bottom one is the A0 point. If I like this solution, I need to remember those numbers. And then what do I do once I have this? I go get another one that's different so I can have a full mechanism. And I remember those A0s and A's. But wait a minute. Shouldn't I call one of them B's instead of A's? Because one's an A side, one's a B side. Yeah. Do I need to go modify my Mathcad so that I change the name of my variable from A to B? No, because it's the same equations. But I need to have an A side, I need to have a B side. What's the next logical step? And it's not in this document. Take that to a 4-bar position analysis document. What do we start a 4-bar position analysis document with? A0A, B0B, and P. What P would we be talking about? P1. But shouldn't we also go to that 4-bar document, 4-bar position analysis, with this stuff? The fixed point locations. This is the thing we're moving in position 1. Can we use rigid body motion stuff to animate the whole landing gear thing in the 4-bar document? You bet we can. So all the skill you learned in the 4-bar, in the position analysis, you did a 10-bar or whatever, but we'll go back to 4 bars now. All that skill that you learned, we then take the answer out of here, bring it into a good 4-bar analyzer with good graphics attached, and we find out if it works right. Okay, we actually watch a movie and see if it passes through all 3. Okay, it's also a very good idea to draw this thing in the 3 required positions. That way you can watch the movie and see if it passes through all 3. So we not only want to draw this thing moving, we want to draw it in its 3 required positions. Rigid body motion would let you, or rigid body drawing would let you do that. We would just need to draw this in 3 positions by moving it to a new point and rotating it through the angle alpha. That's the technology of dyad synthesis. You think you're ready to do it? I will give, what will I need to give you to start this? I need to give you a picture of the thing we're going to move. I need to give you the legal and illegal spaces. Probably need to tell you which point in 3 positions, and I probably need to give you 2 alphas. Or I need to give you a picture so you can measure the 2 alphas. I give you that picture and I give you some point data. You can go through this synthesis stuff. We will pick this up when we get back from spring break. I will see you.